All right, so today we're going to take a look at 7.3. So we're going to get away from inverse trig a little bit and just talk about solving trig equations and inequalities graphically. So we've done this kind of thing before. It's like you put something in y1, y2, calculate an intersect. Or sometimes you get everything on one side, get it equal to 0, and calculate a root, or calculate a 0. Either method. But the key here is going to be we're focusing on trig functions, which means they're periodic, so we have infinitely many answers. And we're going to look at problems where maybe we have higher powers in the problem. Right? Something that algebraically this could be very difficult to do. Maybe not. Maybe it would be. It depends. But graphically, we know we can solve any kind of problem because we don't have to worry too much about the algebra. What we do have to worry about is representing all solutions. So we're going to have to figure out what is a formula for the period when you square cosine or when you cube cosine. Is it still 2 pi over b? Or does it change it? So we'll take a look at that. And by the end of today, you'll have a formula to figure out the period for any trig function raised to any power. Okay. All right, so just a kind of a little recap, and we've done this before. To find solutions to trig functions, first thing you want to do is set your window to be 1 cycle wide. And then find all the solutions in that period, or that cycle. Once you find all the solutions in the specific window you're looking at, you take into account all solutions by putting plus the period times n, where n represents an integer. So the important thing here is you've got to figure out the period of your trig of your whole problem. Now, if you only have a single trig function in it, that's easy to figure out the period. If you have one like I showed before, you've got 3 different trig functions, maybe some are squared, cubed, you've got to figure out the period of that whole thing. So that's a little bit more work, but not too bad. So let's start off with a nice, simple, single trig function equation, no exponent, and solve it graphically. Algebraically would be a lot faster, but I want to kind of get back in the graphical mindset for this section. So sine of x equals 0.8. Can someone tell me how I would solve this graphically? Yep.
And why wouldn't we put sine of x and then why should you put 0.8?
Put 0.8. All right. What should I do next? Yep.
You should set your window to what period.
Yep. Set my window so I'm looking at exactly 1 cycle. If you look at less than 1 cycle, you could miss answers. If you look at more than 1 cycle, you might be looking at extra answers that you don't need to. So set it to exactly 1 cycle. What's the period of sine without any transformations? Yep.
Negative pi 2 to pi 2.
Can you give me just a single number for the period?
Pi. No.
That's for tangent or cotangent?
Man, I'm not thinking.
Okay.
2 pi.
2 pi. So you can set a window however you want of 2 pi, but you got to set it so it's 2 pi. What would be one way to get a window that's 2 pi units wide? I need a min and a max. Yep.
You could do the min of 0 and the max of 2 pi.
Yep, we could just do 0 to 2 pi. We could do negative pi to pi, but I would just do that. Okay, so we've got that. Range, what's the high and low for sine? Yep.
1 and negative 1.
So we're covered with negative 3 to 3. I think we're good. I don't remember if I typed in 0.8. I think I did. All right. So first thing I like to do is figure out how many answers I have per cycle, which in this case is how many? 2. So we're going to have an x1 and an x2. These are approximate. They're not exact. And how do I find each one of them? Yep, calculating the intersect. So if we do second calc intersect, You just hit enter 3 times. We'll get one of them randomly. 2.21. Now we need the other one. We're going to be a little more careful. Should be good. 0.93. The direction said find all the answers from 0 to 2 pi, you'd be done. But it doesn't. It says find all. So how do I represent these two solutions repeating forever, left and right? So
Plus 2 pi n.
plus 2 pi n. And remember, what does n represent? Yeah?
Number of cycles.
The number of cycles, which has to be an integer. Okay, you can add 6.28 to any one of these numbers as many times as you want, and you'll get an answer in the next cycle. Okay, questions on that? So that's the basic idea of what we're doing. We're just going to start looking at equations that have a little bit more going on. Now in that problem, I told you there's 2 ways you can solve these kinds of problems. You can put something in y1, something in y2, and calculate an intercept. Or, if you move everything to one side and get 0 on one side, then what you're doing is solving for the roots. Okay? Either approach could yield the exact same result. Right? It's just a different way of doing the same thing. So for some of the problems in this section, I think most of them, we're going to get everything on one side and get it equal to 0. Does anybody remember what kind of equations do you solve by first getting it equal to 0? Yeah?
Quadratic.
Quadratics. And if you look at one of the problems that we're going to do, it kind of looks like a quadratic. And that's because eventually I'm going to show you how to solve this with the quadratic formula. Not today, but at some point we're going to come back to it. And the first step is getting it equal to 0. And it's actually not that hard to solve this with the quadratic formula. It looks a little different than what you're used to because it's trig, but you can still use it. And I'll show you how. But that's not this week. So remember that the idea is if you're solving an equation that's a periodic function, when you get it equal to 0, you're solving a periodic equation. Periodic equations mean that there are infinitely many answers or there are no answers. One of those two things has to happen. So if you have a term in your equation that's periodic, that's called a periodic function. By putting that in an equation, now you have a periodic equation, which means you need to put plus the period times n when you solve. All right, so this is really saying the same thing I've said at least 2 other times this week. If you set an equation equal to 0, and let's say that it has n solutions. The last problem we did had 2. You have to find all the solutions within one period first, just like we did. So you find x1 and you find x2, just like that. Once you find all the solutions within one period, you represent them in general by putting that solution plus the period times n. Just a reminder that p stands for period and n is an integer. It represents the number of cycles. Okay, we've gone through this a lot. I'm just putting it up there again in case anybody is still confused on that. And you have to do all the solutions. So if you look at one window and it has 17 solutions, you do have to write every one of them. We're not going to have one with that many, but if you did, you got to do it. Okay, we might have one, I think, with up to 5 or 6, which means you have to do second calc intersect or second calc 0 5 or 6 times. And it's not really harder, it's just longer. So questions on that idea? So how do you find the period of a more complicated trig? In fact, I don't even want to say function here. Let's say equation. So an example of a more complex trig equation would be this one. There are two periodic terms in this, cosine squared and sine. You have to find the period of each one that I underlined separate. Okay. The second one I think everyone should be able to do, find the sine of t. That's just regular sine, no transformations. Cosine squared, a little different. So we'll have to talk about that one. The one doesn't have any effect on the period at all. That's not a periodic term, that's a constant. So when we're looking at finding the period, the first step is just to focus on the trig functions. Don't worry about numbers. Numbers don't matter. So find the period of each periodic term. A periodic term is a trig term, not a constant or anything like that. And then once you know the period of each individual trig term, the period of the whole thing is the least common multiple of the individual periods. A lot of times it comes out to pi or 2 pi. Those seem to be the numbers it comes out to quite a bit. So, for example, let's say you had two periodic terms in an equation, and the first one had a period of 2 pi, and the next one had a period of 3 pi. And you say, well, how often is what is the period of the whole equation? It's going to be the least common multiple of these two. This one repeats every 2 pi, this one repeats every 3 pi. So how often would the entire thing repeat? Every what pi? Yep.
6 pi.
Every 6 pi. So once you get to 6 pi, you'd be having a repetition of what you had before. Because both of these, you have to take into account both of them. It's the least common multiple. All right, let's try that. So right now, we don't have a formula for finding the period of a trig function raised to a power. So let's just kind of play with it and graph it and see what we think it is. Let's graph just cosine squared. I don't want to complicate it with anything else. I want to see if I can figure out the cycle length of cosine squared. And how you type cosine squared in is like this. There is no way to type it in the way you're going to see it on paper. Whenever you raise a trig function to a power, they usually put the number right between the argument and the trig function. Well, on a graphing calculator, that means to do it like this. Very important you close that parenthesis and make sure the 2 is on the outside. If you type it in like this, you're not doing cosine squared. You're squaring the argument and then taking the cosine. That's not what you want here. Okay. Any question on how I type that in? Now let's set a window that we know. Okay, let's do 0 to 2 pi, and let's look at cosine squared. How many cycles of cosine squared do you think we're looking at there? Yep.
2.
2. We're looking at 2. Here's 1. There's 2. And what was my window again? From 0 to what? 2 pi. So if from 0 to 2 pi, you're seeing 2 cycles, what do you think the length of a cycle is for cosine squared?
Pi.
It's pi. the length of the cycle for cosine squared is pi. Now again, I'm going to give you a formula in a minute to figure that out. But we didn't really need the formula. We could just graph it, look at it, and go from there. How about sine t? That one we shouldn't need to graph. Yep.
2 pi.
2 pi. So the first periodic term is going to repeat every pi units. The second periodic term is going to repeat every 2 pi units. So what's the least common multiple of 1 pi and 2 pi? Yep.
2 pi.
2 pi. So that means when we graph this entire thing in y1, which we're about to do, it's going to repeat every 2 pi units. Now, let's type in that whole thing. So we've got 2 cosine x squared plus sine of x plus 1. And I'm going to set my window to be exactly 1 cycle. Now I should probably set my range a little higher. Yeah, my range -3 to 3 isn't good enough. I would do at least +4. Doesn't look like it goes lower. Set the window +4. Good. And that's what this graph looks like. That's the pattern that's going to repeat itself every 2 pi radians. So if you took this and you wanted to know what it's going to look like, try again. Okay. So what's it going to look like if you were to zoom out and look at, say, 0 to 4 pi? It would look just like this. I'm trying really hard. It's the effort. Close enough. But that's what it's going to look like. That's the pattern that you're going to keep getting that repeats itself. So it should always end exactly at the same height that it started at. Otherwise, when you graph the next cycle, it wouldn't line up. All right, so now the question is, where is this equal to 0? So are we calculating an intersect, or are we calculating a 0 in this one? Yeah?
0.
We're calculating a 0. So if we look at the graph, the only question I have, and it's mainly because I traced over it, is does it dip below there and cross twice? So what I might want to do is I can tell it doesn't hit 0 anywhere else. This is the only area I kind of want to check out a little bit. What could I do to check that out and see if it's actually crossing once or twice? Yeah?
Find the minimum.
Well, I know the minimum. Okay, yeah, find the minimum, because if the minimum is negative, then you know it must be crossing twice. If the minimum is 0, then you know it only crosses once. Yeah, it's a great idea. Okay, so let's pick a point to the left. Pick a point to the right. It's way bigger than I needed. And the minimum is 0. Okay, it's giving me it in scientific notation, but it's 0.0 10 times, and then a 2. So this does not go below 0, which means it's only going to touch the x-axis and then bounce off it. And that happens exactly at 4.71. How often is that answer going to repeat itself? Yep.
2 pi n.
Every 2 pi. There you go. So this particular problem only had one answer per cycle. Questions on that? Okay. Let's try this one. do here to get this problem set up more like the last one? We could solve it this way, but I'd rather solve it the way we did the last one, which means we need to do what? Yeah?
We need to subtract tangent x.
Yeah, let's subtract tangent x. So now it's equal to 0. And next thing we have to do is find period of each independent periodic term, and then give me the LCM of all of them. No powers here, so we don't have to worry about that. What's the period of cosine? Nick?
2 pi.
2 pi. What's the period of tangent? Yep.
Pi.
Pi. And LCM of 2 pi and 1 pi. Yep. 2 pi. So whatever we get for an answer here, it's going to repeat itself every 2 pi. All right, now let's graph it. So we have 3 cosine x minus tan x. Okay, window's fine, 0 to 2 pi. What do we know about the range of tangent? I know the range of cosine is negative 1 to 1. What's the range on tangent? Yep.
Negative infinity to positive.
Yeah, it's negative infinity to positive infinity, which means that this graph is going to go off the screen. Okay. So what I would do is, you're not going to be able to go, obviously, to negative infinity to positive infinity, but maybe negative 8 to 8. That should give you a pretty good idea of what's happening. So let's hit graph. And that is the pattern we get that would repeat itself over and over. Notice what I said before. It ends at exactly the same height that it started at. So the next cycle would be nice if all that stayed together, but the next cycle of this graph, my smartboard is not working super well. It looked like that. That's the pattern that you're going to see that keeps repeating over and over. Okay. How many answers do we get per cycle in this problem? Yep. 2. So we're going to do x1, x2. Okay, I'll do x1. If someone could find x2, which is after the first tick mark, that will just speed us up a little bit. So second calc, 0. I'm going to move my cursor till I get over there. So the first answer that we get is 1.01. And that's going to repeat every cycle. And how about the second answer? Tim?
2.13.
2.13. And that repeats every cycle. All right, so when you start combining multiple trig functions together, you start getting some more interesting kind of graphs. They still have a pattern to them and they still repeat, but they're not as nice of a wave. They're more complicated patterns. Questions on that one? Okay. So I think what would be helpful at this point is, before we do this one, we need to kind of start looking at, all right, what if we have cubed, or to the 4th power, or to the 10th power? There's a pattern for figuring out the period. So I'm going to show you a table, and it's going to involve 2 formulas, 2 pi over b and 1 pi over b. And those 2 formulas, I showed you that you can use them when you have trig functions to the 1st power. But you can actually use them when you have trig functions to higher powers. You just have to know which one to use when. Right, I'm going to show you. there's a formula that you can use in any of these cases. So this covers a lot of cases. First of all, this formula is going to cover all the tangent and cotangent problems. Doesn't matter if you raise it to an even or an odd power. And it will also cover all of the cases where you raise a trig function that's not tangent and cotangent to an even. Yeah?
What about 1?
Well, that would be to an odd power. So we'll talk about the formula if you raise sine, cosine, secant, or cosecant to an odd power next. For this particular case, the formula is pi over b. So this covers tangent and cotangent completely, and it covers the other 4 to an even power. And I put absolute value of b because remember, if b is negative, that causes a horizontal reflection. But when we're talking about period, that's a length. You don't ever want to give me a negative number for length. So the other case we have is sine, cosine, secant, and cosecant to an odd power. Do people have what written down when this formula works? So the other one you're going to write is just the other cases I haven't written, and it's 2 pi over d. That's when the other formula works. So that's sine, cosine, secant, or cosecant to an odd power. 2 pi over the absolute value of b. So now you've got a formula to figure out the period of any trig function raised to any integer power without having to graph it. Okay, you could always graph it if you forget which formula you use for which. Like you're like, I don't remember the formula for sine cubed. Okay, graph sine cubed in y1 all by itself. Set a window from 0 to 2 pi and see how many times it repeats itself. All right, so now that we have these two formulas, let's go back to the problem we were doing that has sine cubed, and we should be able to figure out the period of that without graphing it. We can just use our formula. All right, so sine cubed 2x. Okay, a couple things going on. The cubed is going to affect the period, and the 2 is going to affect the period. So let's start with sine cubed. What's the formula that we use to find the period when it's sine to an odd power? Michael?
2 pi over the absolute value of b.
Yep, sine to an odd power is 2 pi over the absolute value of b. So 2 pi over, what's b in the sine cubed argument? Yep, 2. So that means sine cubed 2x is going to cycle every pi units. How about cosine x? That's technically cosine to the first power, so you could think of its cosine to an odd. John?
It'll be 2 pi over b as well.
2 pi over b again.
And then the b is 1.
And b is 1. So what's my least common multiple
2 pi.
between 1 pi and 2 pi? Yep, is 2 pi. All right, now we just have to graph it. Be a little careful with parentheses here. So we're doing 3 sine cubed 2x. Okay, here's how you type it in. You don't want to cube the 3 in front. In other words, you don't want to turn this 3 into a 27. So type it in as 3, and then let's put parentheses around what we want to cube. Sine 2x, close the parenthesis for my 2x, I don't want to cube that. If I did that, I'd have 8x cubed as the argument. That's not what I want. I want to do the sine of 2x. After I do that, I want to cube it. And after I cube it, I want to triple it. Okay, so that's how you type it in. Second argument, that's a little easier. 2 cosine x. And check your window. Again, 2 pi is the same cycle we've had for the past couple problems. I think negative 8 to 8 is probably going to be more than you need for your range. We can try it, and if it's too squished because we're zoomed out too far, we'll zoom in a little. But let's give that a shot. Yeah, I probably could have gotten away with like negative 3 to 3. Or maybe negative, okay, maybe negative 6 to 6. There we go. And that's the pattern that's going to keep repeating. Double check that where you end is exactly the same height where you started. So they would connect if you copy and pasted it. That looks good. Now, unfortunately, how many solutions does it look like we get here?
6.
Yeah, looks like we're going to get 1, 2, 3, 4, well, 1, 2, 3, 4, 5, 6. Right, which a little bit tedious because we'd have to calculate the zeros all those times. So I happen to have the answer already done. So the answers that we're going to get are 0.5. We're going to get 1.25, 1.57. Going to get 1.89, 2.65. And 4.71. And each one of these answers is going to repeat how often?
For 2 pi n.
Every 2 pi n's. I'm just going to do a big plus 2 pi n on all of them. Yep.
So the x max in the window was 2 pi, right?
Yes.
Alright, so I must have wrote something wrong.
So every one of those answers has a plus 2 pi n on it.
Do we have one of those in homework?
With 6, I don't think you have one with more than 6, but I don't even know if there is one with that many. Again, I don't think it's harder, it's longer. You got to calculate all the zeros. Some graphing calculators might give them all to you at the same time. I don't know if the Desmos calculator can give you all 6 at once. If that was the case, then that's easy enough. But the ones I have don't. Not sure if the TI Inspire, a little bit more advanced than the ones we have, those might give it all to you at once. I don't know. All right, so questions on that one? All right, so now let's go back to one of these for a second. And let's look at I want to look at a simple one. That's a good one. Let's say that I asked you not where it's equal to something, but maybe where it's above something. Let's say I wanted to know where it's above 0. Well, that would happen from here to here. In that particular interval, I mean, it looks like that's 0 to pi, because I think the window was 0 to 2 pi. So from 0 to 2 pi, or 1 pi, it's above 0. Above or equal. We'll say above or equal, because I use brackets. How often is it going to be above or equal to 0? This interval is going to repeat how often? Yeah?
Every 2 pi.
Every 2 pi. So if you look at 2 pi to 3 pi, that's the next time you're going to see it above 0. I mean, if you add 2 pi to that, that's the next time. So when we're solving an inequality, the only difference is we're finding an interval, and instead of a single number repeating every cycle, you're going to have an entire interval repeating every cycle. And that's the last thing we're going to look at. Okay, solving some inequalities. All right, so to solve an inequality, the first thing you have to do is basically what we've been doing. You've got to find some intersections. So first, find the solutions that you would find to the equation. If you want to know when it's above 0, well, first find when it would equal 0. And then once you have those intersection points or those roots, then you can build an interval from that. But when you're solving an inequality, most of the time your answer is an interval. You do have to keep in mind vertical asymptotes. If you have a vertical asymptote in the middle of a problem, in the middle of your interval, that breaks your interval. Then you have to put the union symbol and start again. Let me just go back to an example of that. So something like this. If I asked you where this particular graph is below 0, you could say from this point, which you'd have to find, up to the vertical asymptote. So it keeps going down forever until it hits that vertical asymptote, and then all of a sudden it jumps back up. And then another interval where it's negative is from here up to that vertical asymptote. So there's 2 intervals per cycle where this graph is below the x-axis. Interval 1 from here to the asymptote, and interval 2 from here to the asymptote. Right, so asymptotes can be a little tricky to find in a more complex trig function, so usually they're going to be pretty obvious what they are, like a nice number like pi. It's not going to be a tricky value to figure out. You'll be able to see it clearly. So let's find where sine is less than cotangent. Now we can do it 2 ways. We can type in a y1, y2 and do an intersect. Or I think let's stick with the way we've been doing it. So we can just continue that line of thinking. Let's get 0 on one side. All right. So what could I do here to get 0 on one side? Yeah.
Subtract sine of x.
Sure. So cotangent minus sine. Okay. All right, cotangent. How do I type that in? Yeah.
1 divided by tangent.
Yeah, that's one way to do it. 1 divided by tangent. So there's my cotangent minus my sine. Now, I'm looking for where this graph is above 0. That's what I want to know. Where is this graph greater than 0? So, let's see. First thing is I should check my cycle. What's the cycle of cotangent? Yep.
Pi.
Pi. What's the cycle of sine? John?
Would it also be pi?
Nope. Sine does
Oh,
not
sorry, no.
cycle every pi.
Pi.
2 pi. And what's the LCM?
2 pi.
2 pi. That's why I was just kind of jumping to the graph, because in my head I had already looked at that quickly and I saw it was the same. But it's not a good idea to do that. You should check it every time. So it is 2 pi. That's what we've been doing all along. Don't always assume that it is. Cotangent has a range of negative infinity to infinity, so we're going to end up with asymptotes. So we're going to look for where this graph is below the x-axis, but watch out for any asymptotes. Looks like I have an asymptote dead in the middle of the screen, so that's easy to find if we know it's 0 to 2 pi. And it looks like I have another one on the right edge of the screen, and I have one on the left edge of the screen. Now, if you look at that quickly, you might say, looks like you graphed 2 cycles. They look exactly the same. Can people tell these 2 graphs are not exactly the same? They are curves, but like, I don't really know how to explain it. They're different. I mean, the easiest thing I could do on the smartboard is this. They're close, but they're not exactly the same curve. Okay? So that is 1 cycle, not 2. All right, and we want to find where we are above 0. Let's just trace that up. That's from here up to there, and from here to there. Interval 1, interval 2. Okay, where does interval 1 start? That's my x value, bless you. Michael?
Wouldn't it be 0 but with a not bracket parentheses?
With a parenthesis, yes. Interval 1 starts at 0, not including it. And you might think, well, wait, yeah, we always include 0. No, not here. That's a vertical asymptote at 0. Can't use it. Up to, we need to find that intersection point. Or, I'm sorry, we need to find that root. So let's do second calc 0. And we'll just get over there. 1, 2, there. All right, 0.90. Now we have to decide, do we include or not include 0.90? Yep.
You include it
Why?
because it hits it.
So does it say we can be equal to 0, or do we have to be above 0?
Above.
We have to be above. At 0.90, we hit 0. So we don't want to include that. The only way you'd include the 0.90 is if you have this. But we don't. All right. Now, interval 2. Interval 2 starts at an asymptote. What does it look like the asymptote is? Michael?
Pi.
Pi. You could always confirm that by going to your table and trying to type in pi. Type in pi, and you get an error. That proves that pi is an asymptote. So it starts at pi, never include the asymptote, and where it ends is right there. So let's plug that in. Let's find the root. Second calc 0. You gotta get over to the other piece of it. Takes a second. So we got that somewhere around 5, I think. 5.38. Including or not including the 5.38? Not including. Now, don't forget the easiest part at the end here. That's where the function is above 0 in the first interval. How often do each of these intervals repeat? Yeah? Every 2 pi. So if you were to add 2 pi to all these numbers, you'd get the next set of intervals in the next cycle. So what we want to do, and the way I'm going to do it, is just put a plus 2 pi n on that whole interval, and a plus 2 pi n on that whole interval. And again, what that means is to add multiples of 2 pi to every single number that you see. Okay, any question on that? All right. Let's try let's see, what's this? Alright, let's do this one. And let's graph this one as is. In other words, don't rearrange it. Just do a y1 and a y2 type thing. We've got sine 2x, and we've got x squared minus 1. I want to know where the sine function is above this parabola that's been shifted down 1. Okay, let's think about the window. Well, you know what? Let's just do zoom 7 this time, because I want you to see something. There's your sine function. Repeats forever. There's your parabola. Does your parabola repeat forever? No. Parabola happens one time and it's done. So what that means is when we find all solutions, you're looking at them all right there. It's not like this parabola is going to repeat again off the screen, and then you're going to get another interval of solutions later on. No. This is different. This is periodic. This isn't. So when you mix something that's periodic and something that's not, you only get one interval that's a solution. There's no plus 2 pi n on this. We just have to see what they want us to find. Where is the trig function above or equal to the parabola? All right. So where is the trig function above or equal to the parabola? That's going to happen from here to there. That's the only place that the trig function is above the parabola. Everywhere else, the trig function is under the parabola, because the parabola goes up so fast. Any question on that one? Or how you would do it from here? Just calculate these two intersections. Why would I be able to use a bracket on this one? Yeah?
It's above or equal.
Yeah, because it's greater than or equal to. All right, so one last thing. We still have about 10 minutes. I have one last thing I do want to show you. And that's it. So it's a double inequality. So really not that much different than a single inequality. You're just going to be graphing three things. And usually what you're going to be looking for is where something is sandwiched between two other things. That's a double inequality. And a lot of times with the double inequality, I just graph it as is. That's the simplest way to do it. We're going to have a left, a middle, and a right. So do a y1, a y2, and a y3. And you're usually looking for where y2 is sandwiched between y1 and y3. All right, so y1. Well, you know what? I'll try to do the right colors once I know where I'm putting them.
Did you?
So negative x, x sine x. What does this do when you multiply by a number in front? What kind of transformation is that? Yeah?
Vertical stretch.
It's a vertical stretch, and in this case, it's a variable vertical stretch, which means the vertical stretch changes depending on how far away you are from the origin. So it's not a constant vertical stretch. So it's going to make it look a little interesting. And x. So let's see what we got. This one is blue. The middle one is red. And the one all the way on the right is black. So I'm looking for where the red function is sandwiched between the blue and the black. That's what I'm trying to find. Above the blue, below the black. Okay, let's do the zoom 7 and see. So there's a line with a slope of -1. There's my trig function, which has a variable vertical stretch. And there's my other line with a slope of +1. Might help if I zoom out. Let's go zoom. Don't turn on. Let me. There we go. Calculator speed 400. It's going to graph real fast.
Gotta do that.
No, sorry. Yours can't do that.
Why don't you just leave it on that all the time?
It defaults back to what it was always.
Whoa.
So there's our graph. We're looking for where we are above the blue and below the black. Can anybody tell me where is the red graph above the blue and below the black? John?
On that right-hand side, the small little section there that like intersects the black and
Can you give it to me as an interval?
try. What is the period of the window on this?
It doesn't really matter what the period is here. I could zoom out more, but you're going to see more of the same.
Yeah, I mean it looks like I don't even know how to describe that.
Caleb?
Would it be open bracket 0 to infinity?
So, yeah, bracket 0 to infinity. Anywhere on the right-hand side of this graph, you are above the blue and you're less than the black. Less than or equal. That's why you can use the bracket. On this side, when you're below 0, it's the opposite. We don't want that. That's where you're below the blue. No, we want greater than the blue. So that's a double inequality.
It's an hourglass.
What's happening in the center? It's like I can't really like see, but it looks like a circle.
It's connected. It's just, if I can move my cursor off.
Oh, is it just the curve? Okay. Yeah, because it looks like it doesn't reach 1, like the trig function.
Yeah, it goes right through the origin, and then it's a reflection of what's on the left.
It's a really crazy graph.
Mr. Hager,
Yeah.
can you just scroll up real quick?
Yeah, it's a variable vertical stretch, so essentially the height of it approaches infinity as you head further and further left and right. And as you get in towards the origin, it starts to oscillate very short. All right, so that's the problems for tonight. So that's 7-3. You'll need a graphic calculator for most of it, and then tomorrow we'll finish up everything for the week with 7-4.